Here we consider the function a of x equal to p times the quantity 1 plus b times x to the power m times the quantity 1 minus x to the power little n, which models the final value, a of x, of a bankroll after capital N equal m plus little n consecutive wagers on an event with given odds of b to 1 against. So in this model, the true odds are m to little n in favor of the event. In other words, m represents the number of wins, little n is the number of losses, and capital N, which is m plus little n, is the total number of wagers. So that value p represents the initial bankroll, and x represents the fraction of the bankroll wagered at each of the capital N consecutive events. So in this example, we seek the value of x on the closed interval 0 to 1 that will maximize a of x for given values of p and b and m and little n. Suppose the initial bankroll is $3,000. The true number of wins is m equal to 48. The true number of losses is n equal 13. And suppose that b is 0.92. Find the value of x that will maximize a of x on this closed interval 0 to 1. Now I can think of several different approaches to answering this. And of course the first thing is just a sort of a graphical and numerical approach. You could just type the function into a graphing calculator or a computer and look for the maximum and identify it that way. The disadvantage there is that if you don't really know very much about a function in general, you may not recognize whether or not you've got the window set correctly to find the maximum. It's possible that there could be a value where the function reaches a higher point outside of the window that you've set, and there's really no way to get around that in general for a function that you're not familiar with. So if you're very familiar with the shape of the curve, you know where the maximum should be, then you might just go with a graphical numerical approach. But it has its limitations. The other methods that I've listed here all are guaranteed to identify exactly the maximum and work in any situation, regardless of what the function would be. They're general approaches that are analytical, whereas this is a kind of numerical approach that may work in some specific cases. These are much more general and analytical, lead to exact values, and confirm that they are the only possible answers. There aren't other possible answers outside of the window that we might be looking at through a numerical approach. Okay, so we could go straight to the product rule and power rule and just do a derivative of this function, and I think I'm going to do it that way. I'll just leave these other methods for another time. Logarithmic differentiation is this is a nice example to see how logarithmic differentiation could work. And the Kelly formula only works specifically in this scenario with functions of that type. So it's not a general approach, but it's really an interesting way of answering this specific question. But I'd leave that for another video another time. Okay, so to answer this specific one, let's look at the values that are given. So we have this value, 3,000. That's the value capital P. Of course, we have m equal 48. We have n, little n equal 13. We've got b is 92, or 0.92. So let's put that into this function here. So the function would look like this. It's 3,000. 1 plus, we've got a 0.92 times x to a power 48. And then 1 minus x, and that's to a power 13. And if we're trying to find a maximum in general for some function like this where we can find a derivative, we'll use the derivative to find a critical point, and the critical point is a potential max or min. So let's take it that way. That's kind of direct, most standard way of handling a question like this. So doing the derivative. So here we go. We'll get a prime. We're looking for critical points, so we'll get the first derivative. So we could just take that 3,000 as a constant and just multiply times the derivative of the product here. And so it's a product rule, right? So this is a factor u and this is a factor v. So I'll do the derivative of the factor u. If I call this u and this v, then the derivative of u, well, the 48 is going to go down in front as the power rule. As we follow the power rule, we get 1 plus 0.92x to a power 47, and then the chain rule would produce a factor of 0.92, and then I have to copy this 1 minus x to a power 13, and now we're running out of space. So what I have right there is u prime times v. And after you do u prime times v, you have to do u times v prime for the product rule. So now we could write down 1 plus 0.92x with a power of 48, and now we're doing the derivative of v. Multiplying with the derivative of v, well, the 13 would move in front as the power rule. 1 minus x, we'll subtract 1, that gives me 12, and then I get a chain rule factor of negative 1 there. So what I have here is the factor u, and all of this is v prime. Now that I have the derivative here, what I'll do is just recognize that I've got a constant factor 48 and 0.92. I'll multiply those together and leave these other factors as they are. And then I've got this 13 and this negative 1 factor, so I'll just put that there at the beginning of this second term in the expression as a negative 13 times these other factors that are there. And now we're just looking for when is this derivative equal to 0. At this point, maybe I'm looking for anything that's in common that we can factor out in front. So sure, let's put 1 plus 0.92x with a power 47, because of course I have 1 plus 0.92x to the 47 power, and here to the 48 power, so the greatest common factor in this term and that term is with a lower power, 47. That's what's in both terms, right? Just 47. And then I could also factor out 1 minus x with a power 12, because that's the lower power, looking at this whole term and then minus this whole term. They both have a 1 minus x, but to a power 12 only in common. So then what's remaining would be the 44.16, and there would be a single factor of 1 minus x from the first term, because I just took out 12, and there were 13 factors there. So there's only one left, minus, and then looking at this term, as I factor out these two factors out of these two terms, what would be left is minus 13, 1 plus 0.92x, and that's it, because I'm factoring out 47 factors, and there were 48 there, and I factored out 1 minus x to the power 12, which is all I had there. So that's what's left when you factor out those two common factors. Again, my goal is to find critical points, actually critical points only on the interval 0, the closed interval 0 to 1. So my derivative now is looking like this. What I'll do is just multiply this out, so it becomes, and multiplying that 13 through, 13 times 0.92 is 11.96. Now we have like terms. These are constant terms. Those are both terms with x. So let's take 44.16 minus 13. 31.16, and now these two terms are both negative. Okay, so that's pretty good. Now what I'll do is I'll look for any places where the derivative is 0. So I'm solving for critical points. So taking each of these factors, we have 1 plus 0.92x. That could be 0. This could be 0. And of course, this factor. Well, this is when this would require x to be negative. So I'm going to discard that as a critical point on the interval we're interested in, right? We only want critical points between 0 and 1. Here, actually, we would have a critical point at the endpoint of the interval, so we can include this as a critical point or just as an endpoint when we're looking for a maximum value. And then solving this guy, we're solving for x, so we'd have, let's say, 56.12x equal 31.16 when you get rid of the negative, and then x would have to be 31.16 divided by 56.12, and that's about 0.555. And another thing about doing this sort of analytically is that I can make that answer as exact as I want, as accurate as I want, I should say. I mean, that is the exact value, and I can compute a numerical value as accurate as I want now that I know what the exact value should be. All right, so we basically have these 2 points that we would be testing. So without even really looking at the graph, I could say at my endpoints, so I could now collect the critical points and the endpoints and evaluate the function there. And one of the first endpoint was 0. I've got a value of 0.555 approximately, and the other endpoint being 1, which is also a critical point of the function in general. So I'll just evaluate the function at each of those points. So going back and remembering what was the function, it was 3,000 times 1 plus. Okay, and this was the original function that I'm trying to find a maximum for. So I'm looking for a maximum value on this closed interval. I'll test the endpoints and the critical point. So if I plugging in 0, this is going to be 1, this is going to be 1. So we end up with just a value of 3,000 when x is 0. If you plug in 0.555, this is about 3198721 6.87. All right, so about 31 million. And then plugging in a value of 1, as soon as you plug in 1, you realize this guy's going to be 0, and so the whole thing produces a value of 0. So there we have it. Certainly, that is the maximum on the interval. It occurs when x is approximately 0.555. Okay, so that answers the question. I hope that was helpful.